Well, we're going to, in this talk, discuss solving polynomial equations. So for instance, and this is an example, we're not going to do this one right away, we may be asked to solve 6x cubed minus 37x squared plus 32x plus 15 equals 0. Now, there are several things that I want you to know. We would expect this equation to have 3 solutions. It might not have as many as 3, but it would, pardon me, couldn't have more than 3. And the reason I say we expect it to have 3 solutions, we'll see a little bit later, is because the degree of this equation, left-hand side, is 3. And so I'm expecting it to have 3 solutions. But I want to back up a step, because I want you to realize there are several things involved, or several things we discuss that are very similar. They just are, the question is different. So here's solving a polynomial equation. Now, on the other hand, we might be in a position that we're asked to factor, okay? So we might be asked to factor. So we just have a polynomial. This is factoring, of course, and there's a relationship between factoring and solving a polynomial equation. In fact, if we can factor the left side of the equation, then we'll be able to solve it. So factoring and solving are related. If we can do one, we can do the other. That's the idea here. Thirdly, when we're graphing, if we're looking for X intercepts, okay, and I should say find the X intercepts for the function f of x is equal to 6x cubed minus 37x squared plus 32x plus 15. If I were trying to graph this function and I needed the X intercepts, then that would be very similar to what we've done before, because what do we do to find X intercepts? Well, that's when y is 0. And so if we had f of x, which is representing y of 0, then that's the same as solving that very first equation, isn't it? So finding x-intercepts is related to solving a polynomial equation, which is also related to factoring. Those 3 things are much the same, okay? And then there's going to be one other term that may show up in your reading, or I may use it here, and that is finding the zeros of a function. Find the zeros of f of x equals 6x cubed minus 37x squared plus 32x plus 15. Finding zeros. All 4 of these things are the same, because what is a zero? A zero is of a function is an x value that causes the function to go to 0, to be equal to 0. In other words, it's an x value that causes y to be 0. Well, if we're looking for the x values that cause y to be 0, that's the same thing as finding the x-intercepts. That's the same thing as solving that equation in the very beginning. So although the terminology is different all the way through here, what we do is very much the same. Okay, what I am going to do is start with a simpler equation. Okay, so here we're asked to solve, let's say x cubed, I'll say, x cubed minus x squared minus 6x is equal to 0. Now, this is much simpler than the one above, but this will kind of get us started on what we need to do. And so what we recognize, I hope, is that for us to solve this equation, if we could factor the left side, we would be almost there to solving the equation. Okay, so let's, and I notice on the left side that we have a common factor of x, so we'll factor out an x. Now I notice further that x squared minus x minus 6 can be factored, can it? Okay, so we'll factor that. And what would that be? Maybe an x plus 2 times an x minus 3. Won't that do it? And so for our solutions, okay, we set each of the factors to 0. Okay, and in this case, if the first factor x is 0, that means x itself is 0. If x plus 2 is 0, that means x is negative 2. And as x minus 3 is 0, that means x would have to be 3. So we actually have 3 different solutions to this equation. And here's why I said what I did above. Notice the degree of this equation is 3, and the reason there are 3 solutions is there are 3 factors. So usually, not always, but usually an equation of degree n will have n linear factors. Now sometimes those, actually they always do, but sometimes those factors are repeated. So if you have the same factor more than one time, that same factor is just going to give one single solution, although that factor appears more than once. Now, let's notice here, of course, we used the factors. See, we factored to solve. So there's the relationship. We used the factors so we could solve the equation. Now, on the other hand, notice this. If we know the solutions, see, if we know the solutions, so for the solution 0, notice that we have a factor of the original polynomial, okay, that is x minus that number 0, which is just x. That's where that solution came from. If we have a solution that is negative 2, then we can predict that that came from a factor that was x subtract that solution. See, x subtract negative 2 is x plus 2, and sure enough, that's the factor that it came from. If we have a solution that is 3, then we can predict that that solution came from a factor that was x subtract that solution. And sure enough, we have a factor that's x minus 3. So knowing the solutions, we could have told what the factors were. Knowing the factors, we can tell what the solutions are. If we wanted to find the x-intercepts of a polynomial, we would just set the polynomial equal to 0, wouldn't we? Now, x-intercepts are normally going to be labeled as points. So, and notice also, okay, so the x-intercepts here, x-intercepts have a y value of 0. So one of these, because how are we going to find x-intercepts? Well, I didn't do very well here. I should say x-intercepts of f of x is equal to x cubed minus x squared minus 6x. And so what we would do is to say we're looking for the x-intercepts. Well, that would mean y is 0, so that would be a 0 here. But that's the same thing as solving the equation we just solved. And we have the solutions then of 0, negative 2, and 3. We've already done that work. Now, x-intercepts are points, and they're points where y is 0. So the first point has an x value of 0 because that was a solution for x, and a y value of 0. The second point has an x value of negative 2, but of course a y value of 0. And the third point has an x value of, the third x-intercept has an x value of 3 and a y value of 0. But we're basically doing the same thing. Now, one last thing. Zeros of f of x equal x cubed minus x squared minus 6x are the values of x that cause f of x to be equal to 0. Well, if f of x is 0, that's solving that equation again, isn't it? And notice, just as an example, if we use an x value of negative 2, that's a 0 of the polynomial, then that would be, let's see, negative 2 cubed minus negative 2 squared minus 6 times negative 2. When we cube negative 2, we get negative 8. When we square negative 2, we get a positive 4. Negative 6 times negative 2 is a plus 12. And when we combine those, look at that, we get 0. So the solutions to this equation can also be called zeros of the polynomial function, because when we use those numbers in the function, we get a y value of 0. That's the whole lie. That ties it all together. Well, now we want to know how we can go about trying to solve more complicated equations than the one we did here. That is, equations that we have a difficult time factoring. And we'll look at an example on the next page. I think I will go to our original problem. We're asked to solve this equation, but now there's one thing I'm going to do. Okay, here's a hint. 5 is a solution. So, find all other solutions. So 5 is a solution. That means if we put 5 in for x, we're going to get a 0 on the left side. Now, here's the way this hint will help us. Remember the relationship. What's the relationship between solutions and factors? Okay, that's the big thing to remember. Well, if 5 is a solution, then that means what is a factor? X minus the solution, right? X minus the solution 5 is a factor. So x minus 5 is a factor of that long polynomial on the left side. And if x minus 5 is a factor of it, then that means x minus 5 will divide into it evenly. And remember, what we really want to do is to try to factor the left side completely. And since we have one factor already, maybe that will help us complete it. So here's what we would do, is we would divide x minus 5 into. But now, if our divisor is x minus 5, that qualifies for synthetic division, doesn't it? And if we're dividing by x minus 5, the synthetic divisor is the number we're subtracting from x, which would be 5. Okay, now the coefficients of the polynomial, 6, negative 37, all powers of x are accounted for, aren't they? 32, and our constant of 15. So we bring our 6 down. 5 times 6, of course, is 30. Negative 37 added to 30 is negative 7. Now we have 5 times negative 7 is negative 35. Now, by the way, what result are we expecting right here? We're expecting a 0, aren't we? Because we are told by what we've already talked about that x minus 5 is a factor, so it should divide evenly, which means the remainder should be 0. Okay. Well, let's finish going here then. 32 plus negative 35, of course, is negative 3. And then 5 times negative 3 is negative 15. And when we add these together, we get 0. So the remainder is 0. That's what we expect. Now remember, this is the constant of the quotient. This is x to the first, and this is x to the second. So here's what we've got then. 6x cubed minus 37x squared plus 32x plus 15 divided by x minus 5 gives a quotient of 6x squared minus 7x minus 3. That's the quotient. But better than that, that tells us that 6x cubed minus 37x squared plus 32x plus 15 is equal to the divisor, x minus 5, times the quotient, 6x squared minus 7x minus 3. So we've begun factoring. That's the whole power of this division. Now, as we look over here to the right side, we have a trinomial. Then we're pretty good about factoring trinomials. Let's see if we can factor this. And let's see, 3x times a 2x I'm going to try. I need one to be positive and one to be minus because I have a negative 3 at the end. Let's put a 1 here and a 3 here and double check me. But I believe that's correct, isn't it? 6x squared, and then we have a minus 9x plus a 2x is a minus 7x, and 1 times negative 3 is a negative 3. Okay, so now we have it factored. So knowing a solution allowed us to factor completely. So now our equation looks like this. See, we say, okay, we start out with 6x cubed minus 37x squared plus 32x plus 15 equals 0. And we factored the left side as x minus 5 times 3x plus 1 times 2x minus 3 equals 0. And once we have that factored, then we ought to be able to solve, because we simply set each of the factors to 0, don't we? And of course, here at x minus 5 equals 0, we'd simply add 5 to both sides. Here at 3x plus 1 equals 0, first we would subtract 1 on both sides, and then we would divide by 3. Here at 2x minus 3 equals 0, first we would add 3 to both sides, and then we would divide both sides by 2. So the solutions here, isn't that amazing? The solutions to this equation are 5, negative 1/3, and positive 3 over 2. Now a couple other points before we move on. The equation was a third degree equation, wasn't it? The polynomial was degree 3. And from that degree 3 polynomial, we ended up having 3 factors, and that's the reason we had 3 solutions. That's not a coincidence. Usually the number of factors, unless they're repeated, usually the number of factors that we have will match the degree of the equation or of the polynomial that we're talking about. Like I say, in fact, it will have the same number of factors, but occasionally those factors are repeated, and anytime a factor is repeated, we just count the appropriate solution one time. Okay. Now, that whole problem relied on us, and by the way, from here, we could have been asked for factoring the polynomial only. So maybe we didn't have equation, we just factor. And then we would have needed to know that x minus 5 was a factor, and we could have factored it. Now, we're mostly interested in dealing with the process of solving, because when we're solving equations, we need to factor, so that we go through that process. When we're finding X intercepts, we're actually solving equations, and in that we need to factor. So it all is tied together. If we're asked to find the zeros of a polynomial, that's the same thing as solving an equation where y is 0. They're all related. Now, like I said, this all depended on us knowing one solution or knowing one factor to get started. So the next thing we have to be concerned about is, how can we know that? And the truth is we're normally not going to know that, but we can have some values to try. And so we may not know what solution we have, but we know some solutions to try to see if we know some values to check to see whether they're solutions. And when we find out one is, then we can get started like we did here. So let me consider that on the next page. Now we're going to discuss something called the rational zeros theorem, and this theorem gives us some hints of things that might be solutions to equations. So first I want to focus in on the word rational. So here we're talking rational, of course, has ratio in it, and we ought to know now at this stage that a rational number, and that's what we're talking about here, a rational number is one that can be written as a fraction. It's not always written as a fraction. You know, like 0.75 is not written as a fraction, but we do know that it could be written as 3/4. Okay, so rational numbers are all those numbers that can be written as fractions where we have the numerator and denominator as integers. So the zeros, and we're really not concentrating on this concept of zeros. The zeros, remember, are the x values that cause a function to be equal to 0. In other words, zeros are the x values that cause y to be 0, and so that's really solving an equation again, because one side, the f of x, is 0, and the other side is the polynomial. So we might change the name of this as the rational solutions theorem. Okay, and we're referring to solutions to polynomial equations. Okay, that's what we're referring to. Now, I'm going to write this out, so I'm going to come back real quickly here. It'll seem instantaneous to you, but it takes me a bit to write this out, and you don't want to watch me write all this. I wrote this out, as you see, and it's I didn't write it as clearly as I should have. So let's assume that we've got some right here. We've got a polynomial equation. Okay, we've got some ugly polynomial equation. It can be very ugly, and you see some strange notation here. We're assuming the largest power of the largest exponent is n, and that a sub n in front of x to the n just represents the coefficient of that highest power. Okay, and so we're assuming that we have other powers on down to the constant. Now, it may be that some of those coefficients are 0. We may not have a power x. If n was a 5, we may not have an x to the n minus 1 or an x to the 4th term. That would just mean that coefficient 0. All I'm trying to say here is we have a polynomial equation of degree n, and a sub n is the leading coefficient of the highest power, okay, and a sub 0 is the constant. A sub 0 is the constant. So what this theorem says, that if we have a polynomial equation, all rational solutions must be fractions of the form, okay, a factor of the constant term divided by a factor of a sub n, the leading coefficient, okay? Now, it doesn't mean any fraction that we make using those factors will be a solution, but all solutions of the equation will be of that form. So let's just stop and think about our last problem, okay? I've got to look it up again. I'm overlooking it at this point. When we were solving, we're thinking here. When we were solving 6x cubed minus 37x squared plus 32x plus 15 equals 0. What were the solutions? What were the solutions? Well, one of them was 5. Okay, and we can think of that as a 5 over 1. And I'll come back to that in just a moment. One of them was negative 1/3. So let's think of that as a negative 1 divided by a positive 3. And one of them was a 3 over 2. Now, what I want you to notice is that these are all fractions of the form described above. Look at this. 5, that's a factor of, what is our a sub 0 here? It's the 15. It's the constant. 5 is a factor of 15. And although we normally don't talk about 1s being factors, 1 is a factor of the leading coefficient 6. That's the a sub n. Now, when we look at this next one, look at this. 3 is a factor of 6 also, isn't it? Okay, and negative 1, although again, and we have to include positives and negatives here, that's something that's not real clear, but we have to include positive or negatives here. And so -1 is a factor of 15, because we can say -1 times -15 is 15, right? So in the second solution, -1 being a factor of 15 and 3 being a factor of 6, it satisfies this condition that all of our solutions are of that form. Factors of the constant term divided by factors of leading coefficient. Now we have to consider 1s being factors. We have to consider 6s or 15s with the whole number being a factor, and we have to consider the positive and negatives of the factors as well. Well, one more time, let's look at this last solution. 3 is a factor of 15, isn't it? And 2 is a factor of 6. So once again, this is a factor of 15 divided by a factor of 6. All of our solutions satisfy that condition. But there are other, 5 is a factor of 15, and 3 is a factor of 6, but 5/3 was not a solution. So it doesn't mean that anytime you create one of those fractions, you get a solution. It means all of your solutions will be of that form. So it's a tool. It isn't the end of all ends here. That is, we have a place to look for solutions. So let's look on the next page how we would proceed without the hint that we were already given in the last problem. We would have to create our own hint, more or less. Okay, here we're to list all the possible rational solutions to the equation 5x cubed plus 6x squared minus 9x minus 2 is equal to 0. So what we do is we create a list of fractions, possible solutions, rational solutions. And so we're going to have fractions where we have factors of the constant term, in this case is -2, but it wouldn't really matter if it's +2 or -2. 1 or -1 is a factor, and 2 or -2 are factors of 2 and -2 both. So our numerator is going to have one of those 4 numbers in it. Our denominator have to be factors of the leading coefficient 5. Well, the only factors of 5, 1 and 5, but we have to consider positives and negatives. Okay, so those 4 numbers have to be values we use as denominators. So we would look at a list like this. I would probably keep the constant 1. I'd probably stay with a 1 for the denominator, and so I'd have a plus or minus a 1 over a 1, or a plus or a minus a 2 over a 1. And then I'd change my denominator to 5, and so my choices of my numerator are a plus or a minus 1 over 5, and a plus or a minus 2 over 5. So, of course, we would probably simplify. Instead of saying 1 over 1 and 2 over 1, we would probably say 1 and 2. So, plus or minus 1, plus or minus 2, plus or minus 1/5, plus or minus 2/5 are the only rational numbers that have a chance of being solution to that equation. Now, it's not going to have 8 solutions. It's going to have 3 solutions, and the 3 solutions, if they're all rational solutions, would come from that list. So here's the way we would approach it: is we would just start checking. Check. Okay, because once we find a solution, we can probably go on. Well, is x equal 1 a solution? Well, we could substitute 1 in there, couldn't we? And just find out. Okay, and so we would end up with what? 5 times 1 cubed plus 6 times 1 squared minus 9 times 1 minus 2. Is that 0? Well, this would be 5 plus 6 minus 9 minus 2, and sure enough, that is 0, isn't it? Now, another thing we could have done, and so we found a solution, but let me point out to you, because it's not always going to be that easy, and we're not always going to want to check whether 1 is a solution in this fashion, and we might find out that it's not. And how are we going to check the more complicated pieces? So what we could have done is to check to see whether x minus 1 is a factor. See, we could have checked to see if x minus 1 is a factor. In fact, that's more useful to us. Because if x minus 1 is a factor, then that means x equal 1 is a solution. But what we really want to do is factor that left side. So rather than directly finding solutions, what we want to do is indirectly find factors. And once we find the factors and get it factored, then we can solve the whole equation. So the way we would check whether it's a factor is we would use some synthetic division. Now, in this case, we happen to know it already is because 1 is a solution. But if we're dividing by x minus 1, our synthetic divisor is the number being subtracted from x, which is just a positive 1, isn't it? If we write down our coefficients, 5, 6, negative 9, and our constant of negative 2, bring the 5 down. 1 times 5 is 5. 6 added to 5 is 11. 1 times 11 is 11. Negative 9 plus 11 is 2. 1 times 2 is 2. Negative 2 and 2 is 0. And we expected this because that means the remainder is 0. And we were expecting, absolutely expecting, in this case, I'm just double checking something. We're expecting in this case for x minus 1 to be a factor, so it would divide. So here's what we've got now. We started out with 5x cubed plus 6x squared minus 9x minus 2 is 0. And because x minus 1 is a factor, we say, oh, well, now that's x minus 1 times the other factor, which is the quotient, 5x squared. See, that's coming from here, plus 11x coming from here, plus a 2. Okay? Now, the next question is, could we factor further? And I think 5x squared plus 11x plus 2, let's see, how about a 5x times an x? And how about a plus 1 and a plus 2 in that fashion? Doesn't that give us 5x squared plus 11x plus 2? Now, how will we find our solutions? We set each of these to 0. So we really didn't find the solutions directly. We found the factors, so then we could solve. Well, here we get x equal 1. Here, when we subtract 1 and divide by 5, we get x is equal to negative 1/5. And here we have x equal negative 2. Now look in our list above. Positive 1 was a possible rational solution. It is. Negative 2, a possible rational solution. Yes, it is. Negative 1/5, a possible rational solution. Yes, it is. So and now we've solved it completely, and our list, our solutions are in that list. And that list really helped us get started because it gave us the idea to divide by x minus 1 because we thought x equal 1 might be a solution. You know, it wouldn't have always necessarily been. So what if x equal 1 wasn't a solution and x equal negative 1 wasn't a solution? Then we would check x equal 2, and we would do that by dividing by x minus 2. So here you can see we're asked to solve a pretty complicated looking equation, right? Okay. So we're going to accomplish solving that, I'm pretty sure. But what we have to start out with is what are the possible rational solutions? See, we have to have a starting place. Now, what we're really going to do here is we're going to hopefully find a solution by finding a factor. Remember the relationship? We know a solution, we know a factor. If we know a factor, we know a solution. So what we're really going to do is we're going to factor the left side by first finding one solution and then seeing if we can factor further. Finding a solution means we're finding a factor. So possible rational solutions, well, they have to be made up of factors of the constant divided by factors of the leading coefficient. So the factors of 14 are plus or minus 1, 2, 7, and 14. And factors of the leading coefficient, which is 3, are just 1 and 3. So the list is rather lengthy. I'm going to hold my denominator at a 1, and so I'll have plus or minus 1 over 1, which is just plus or minus 1. And then I'll have plus or minus 2 over 1, which is just plus or minus 2. And then I'll have plus or minus 7 over 1, which is just plus or minus 7. And likewise with 14 over 1. And then I have plus or minus, now I'm going to make my denominator 3, so I have plus or minus 1 over 3, 2 over 3, 7 over 3, and 14 over 3. Now, not all those numbers are solutions, but any rational solutions are listed there. And so we might try to see whether x equal 1 is a solution. That is, we're going to see if x minus 1 is a factor. We might see if negative 1 is a solution. That is, x minus a negative 1 or x plus 1 is a factor. And that's the way we would approach this. And I'm going to tell us already that x minus 1 is not a factor. And x plus 1 is not a factor. So now I'm looking at the 2. See, I'm looking at this number 2 in the list. Well, what would a factor be if it was that 2 is a solution? It would be x minus 2. So I'm going to check to see whether this is a factor or not. And I'm going to use synthetic division. Okay? So when I use synthetic division to check whether it's a factor, then my synthetic divisor is the 2, isn't it? And my coefficient's 3, negative 5, negative 23, positive 35, positive 14. Bring the 3 down. 2 times 3 is 6. We add together, we get 1. 2 times 1 is 2. We add together, we get negative 21. 2 times negative 21 is negative 42. We add together, we get negative 7, don't we? 2 times negative 7 is negative 14. We add together, get 0. And this is a big hooray, isn't it? Because that means the remainder is 0 when we divide, which means x minus 2 is a factor. Which also means 2 is a 0, is a solution. But we know x minus 2 is a factor. That's what we just found out. So what we're going to do is, I'm going to write it in here, 3x to the 4th minus 5x cubed minus 23x squared plus 35x plus 14 equals 0. Okay, that's what I need to solve. And with a factor of it, in fact, that means x minus 2 times what? Polynomial. Well, here's the coefficients, aren't there? Okay? It'll be what? 3x cubed plus 1x squared minus 21x minus 7. Now, in this particular case, we don't know how to factor that second polynomial again. So we would just look at another possibility for this polynomial. See, for this polynomial, what are the possible factors? That is, what would be the possible solutions to that part? And so, possible solutions based on that one factor. Okay, well, we would look at the, again, fractions based on the factors of the constant. Well, this time the constant's negative 7, so its factors would be plus or minus 1 or plus or minus 7. And in this case, the leading coefficient's 3 again, so it'd be plus or minus 1 or plus or minus 3 again. And so when we make this list, we'd have plus or minus 1 over 1 and 7 over 1, plus or minus 1 over 3, and plus or minus 7 over 3. So now we only need to consider those values, okay? Now, it may not be clear here, but and you have to understand that I'm just trying to show us how to go through this. We'd have to check to see whether x minus 1 was a factor, x plus 1, x minus 7, x plus 7. We'd have to go through all of these. I'm going to check out for the value of negative 1/3. I'm kind of jumping ahead here, okay? And so that would be what factor? That would be x minus a negative 1/3. So that would be a factor of x plus 1/3, wouldn't it? So now I'm checking out to see whether x plus 1/3 is a factor of the polynomial that we have here. So I can finish factoring this. Well, the polynomial I have here, what are we going to be dividing by? A minus 1/3, because that's what we're subtracting from x. The coefficients now are 3, 1, negative 21, and negative 7. Okay, bring the 3 down. Negative 1/3 times a positive 3 is a negative 1. We add those together, we get 0. Negative 1/3 times 0 is 0. We add those together, we get negative 21. Negative 1/3 times negative 21 is positive 7. Add those together, we get 0. So I'm fortunate here that I found a factor, but I jumped ahead because I knew that. So now what I'm doing is I'm taking this. I already have x minus 2 as a factor, and now what we've discovered is that x plus 1/3 was a factor to that second polynomial. And here are the coefficients to that quotient, which is the next factor. Well, that's a 3x squared, isn't it? 3x squared. And 0x, and then just a minus 21. Okay, so now we look at this and we say, okay, we might have a hard time factoring that piece. Okay, I see we can factor out a common factor of 3. So let's, this is 3 times x squared minus 7, isn't it? So we can put that 3 way out in front. And now we've got a position, now we're in a position that maybe we can solve. Now, we might not know how to factor x squared minus 7 real easily, but what we could do is set each of these factors to 0. Now, we don't set that factor to 0. X plus 1/3 equals 0. And the reason it works here is because x squared minus 7 being a quadratic, when we set that equal to 0, we have lots of tools for solving a quadratic equation. So here we get x equal 2 by adding 2 to both sides. Here we get x equal negative 1/3 by subtracting 1/3 on both sides. And here to solve this, I would add 7 to both sides, and then I'd know x has to be plus or minus the square root of 7. So the solutions, not in any particular order, to negative 1/3, a square root of 7, and a negative square root of 7. Now, a couple of things. What was the degree of this equation? Degree 4. We have 4 solutions. What are the rational solutions? 2, negative 1/3. Those are the only 2 that are rational. Square root of 7 is an irrational number, isn't it? But 2 and negative 1/3 were in the original list, weren't they? See? Those are solutions. And remember, that list is only the possible rational zeros. And so square root of 7 and negative square root of 7 wouldn't have shown up in that list. Now, I may be repeating myself. The degree of the equation was 4, and we have 4 solutions, don't we? Here they are. Amazing that we can do that, isn't it? Well, I think for the purposes of this lesson, I think I'll stop there. We could get solutions that were actually complex numbers as well, so we would just have to deal with those as we come to it. Well, good luck on your homework.